Welcome to the Deep Dive. This is where we take source material you send our way. Could be articles, notes, research, and really dig in.
Yeah, we try to pull out the key insights, the stuff that's genuinely surprising, basically the knowledge you need to get informed quickly.
And today we're plunging into the world of organic chemistry. We're working from some excerpts you provided from a book called Organic Chemistry. Very short introduction.
Right. And we're tackling some big questions here, like what is this field that's dedicated pretty much just to carbon?
How did that focus come about? There's some interesting history there, isn't there?
Oh yeah, involving old theories. And then there's the scale of it all. I mean, the sheer number of possibilities with carbon is kind of mind-bending.
And, of course, the impact. How this chemistry affects all of our lives day to day.
Both the good stuff, the incredible advances, and, well, some of the serious challenges and problems it's created too.
It might sound a bit technical, maybe like a chemistry class flashback for some.
Maybe. But it's really a story that's woven into, well, pretty much everything around you.
So let's get into this material.
Okay.
So the source kicks things off with the basic definition, right? Organic chemistry studies carbon, compounds, their structure, properties, how you make them.
Yep, that's the core. And it immediately contrasts it with inorganic chemistry, which is, everything else on the periodic table.
Which brings up that first big question the material poses. Why? Why does carbon, just one element out of over 100, get its own massive branch of chemistry?
It's a great question to start with. And the answer is kind of twofold. One reason is definitely historical, looking back at how scientists first viewed these compounds.
Okay, the historical angle. Starting with the name itself, organic chemistry.
Exactly. The term apparently popped up back in the 18th century. A Swedish chemist, Torbjörn Bergman, used it.
And his definition was?
He defined it as the chemistry of compounds that came from living organisms, plants, animals, that sort of thing.
Which led to this really fascinating belief back then, didn't it? This idea that stuff from living things was fundamentally different.
Totally. They thought these compounds, these biochemicals, had something special, like a unique spark, or what do they call it? A vital force.
A vital force.
Yeah.
Something you couldn't just cook up in a lab.
Right. They figured only living things could provide it. And they had reasons, They noticed these biochemicals were hard to get pure from biological stuff.
And they decompose faster.
Yeah, much faster than, say, chemicals you get from rocks or metals, the inorganic stuff. So this difference in behavior really convinced them.
Seemed logical at the time, I guess, this almost magical property linked to life itself.
Yeah.
But the source material says this vital force idea didn't last.
No, it hit a major roadblock. And the source points to a key moment, the synthesis of urea back in 1828.
Urea, okay, remind me.
Yeah.
That's found in urine, right?
Yeah.
Definitely a product of a living organism.
Absolutely. So according to that vital force theory, you'd absolutely need a living system, or at least that force to make it.
But that's not what happened.
Nope. The big breakthrough, the real game changer, was that urea was made in a lab, synthesized, simply by heating an inorganic salt, ammonium cyanate. Just heat it up and boom, you get urea.
Wow. Heating a simple inorganic chemical gives you something they thought only life could produce. That must have caused quite a stir.
Oh, completely. It flew right in the face of the vital force idea. It proved you didn't need life or some mystical force to create these so-called organic compounds.
So that led to the definition we use now.
Pretty much directly. Organic chemistry became the chemistry of carbon compounds, full stop. Whether they come from living things or you make them in a flask, it doesn't matter definitionally anymore.
Okay, so the historical link to life gave the name and the initial sort of separate category, even though the core reason the vital force got debunked.
Right.
But the source does point out that even with the theory gone, the link between carbon chemistry and life chemistry is still incredibly strong. We even say carbon-based life forms.
That connection is fundamental. I mean, look at the molecules that actually make up living things. DNA, proteins, sugars, fats. They're all built around carbon atoms linked together. Carbon skeletons.
So even though organic chemistry studies all carbon compounds now, not just biological ones,
it's still the foundation for understanding biology at the molecular level. That's why biochemistry, which focuses specifically on the chemistry inside living systems, is really a specialized area that builds directly on organic chemistry principles.
All right, that clarifies the historical side and the name. But you said there were two reasons carbon gets its own field. What's the second one?
Okay. This is where things get, frankly, kind of mind-blowing. The second major reason is just the sheer, almost unbelievable number of different organic compounds that can exist.
The scale of it.
Exactly. The vastness. Carbon is unique in its ability to form stable chains and rings with itself and other elements, leading to an incredible diversity of molecules.
How diverse are we talking? The source gave a number, didn't it? An estimate?
It did, and it's staggering. The estimate for just the number of medium-sized organic molecules that could theoretically be synthesized is around 10 to the power of 63.
Okay, wait, 10 with 63 zeros after it?
Yep, 1063.
I can't even begin to wrap my head around that. It's just an abstractly huge number.
It is, and the source gives this amazing perspective. That number is so colossally large that there isn't enough carbon in the entire known universe to make even one molecule of every single possibility in that list.
Not enough carbon in the universe. Just for the medium-sized ones.
Correct. Forget the really big molecules or polymers, just the medium ones outstrip the available matter.
Okay. Wow. So that's the theoretical space, this almost infinite chemical universe. What about the reality? How many have we actually, made or identified?
Well, the source mentions that currently researchers around the world have actually synthesized or characterized something like 16 million distinct organic compounds.
16 million. Now, that sounds like a lot on its own.
It absolutely is by any normal human measure.
Yeah.
But when you compare it to that potential 1063,
it's nothing.
Exactly what the source says. It's a drop in the ocean. A tiny, tiny fraction of what's possible.
So there's this effectively infinite landscape of new molecules out there, just waiting to be created or discovered, most of which have never existed before on Earth or anywhere.
Precisely. And that potential is really what fuels so much excitement and research in organic chemistry today. Think about that 1063.
Yeah.
Hidden within that unimaginable number could be molecules with properties we desperately need or haven't even dreamed of. New drugs for diseases we can't treat, amazing new materials, better ways to capture energy. Who knows?
The potential for innovation seems limitless.
It really does. That's the draw for organic chemists, always the possibility of discovering or designing something fundamentally new, something that could genuinely change things.
Okay, so we've got the history, the debunked theory leading to the modern definition, and this absolutely astronomical number of potential molecules. Let's shift gears a bit. Let's talk about what the field has actually achieved over the last century or so. The source really emphasizes the impact on everyday life.
Right, and this is where it becomes very real for everyone, not just chemists. Organic chemistry research hasn't just stayed in academic journals, it has fundamentally reshaped modern society.
It starts with understanding life itself, down at the molecular level.
Which is huge, obviously. But then it extends to providing so many of the physical things we use and rely on constantly. Just look around you.
Like the clothes we're wearing now probably involves synthetic fibers.
Very likely. Or the materials in our homes, plastics, paints, insulation. Even components of the food we eat, like additives or packaging.
The source lists some specific examples: plastics, synthetic textiles like nylon or polyester, perfumes, dyes for clothes and food, artificial sweeteners, synthetic rubber for tires.
The list goes on and on. Products that are so common now, we often just take them for granted. Their existence relies heavily on advances in organic synthesis.
And the source also mentions its critical role in agriculture, right? Feeding a growing world population.
Yes, that's a major one. Organic chemistry developed the insecticides, herbicides, and fungicides that allowed farmers to protect crops and dramatically boost food production over the last century.
Could have fed billions without it.
Arguably not, no. And then there's health, maybe the most personal impact.
Pharmaceuticals?
Medicines?
Exactly. The vast majority of modern drugs that treat infections, manage chronic diseases, relieve pain, extend lifespans, these are triumphs of medicinal chemistry, which is built on organic chemistry, designing and making those molecules.
So the source makes it clear the benefits have been enormous, truly revolutionary for billions of people.
Without a doubt. The improvement in quality of life and life expectancy is undeniable.
But, and there's always a bias in there.
Usually, yes.
The source doesn't gloss over the downsides. It acknowledges that alongside these incredible benefits, the same field has created significant problems, serious challenges. That's a really crucial counterpoint the material raises. Many of these powerful new substances, these discoveries, if they weren't used carefully or if their long-term effects weren't fully understood or anticipated.
They cause harm.
They did. They caused significant health issues in some cases and major environmental problems in others. Think persistent pollutants, unintended toxic effects.
And this, according to the source, has led to a breakdown in trust. a fear of chemicals.
Yeah, it talks about this trend called chemophobia, which it describes as an often unjustified sort of blanket fear of chemicals.
Unjustified how?
Well, it tackles some common misconceptions that feed this fear, like the idea that the word chemical itself automatically means something bad, synthetic, toxic, a pollutant.
When really?
Everything is made of chemicals. Water is a chemical. The air we breathe is a mixture of chemicals. Natural compounds in food are chemicals. It's just a general term.
And it also addresses that common belief.
Yeah.
Synthetic equals dangerous. Natural equals safe.
Right. That's a huge misconception. The source points out very clearly that some of the most potent and deadly poisons known to humankind are entirely natural products found in plants or fungi or animals.
While many synthetic compounds are perfectly harmless, even beneficial.
Absolutely. And crucially, it makes the point that if you synthesize a natural compound in the lab, say vitamin C, it is chemically identical to the vitamin C you get from an orange. Identical molecule, identical property.
Its origin doesn't make it safer or more dangerous.
Exactly. The safety or danger depends entirely on the molecule's specific structure and how it interacts with biological systems or the environment, not whether it was made by a plant or a chemist.
Okay, so that clarifies the chemophobia aspect and the natural versus synthetic fallacy, which leads us to the challenge the source lays out for the future, right? We know many compounds have caused problems, even while providing benefits.
Yes. And the conclusion isn't that we should just reject everything, abandon all drugs, pesticides, food additives, plastics, polymers.
Society wouldn't function as we know it.
It simply wouldn't. We rely on these things too heavily now.
So if rejection isn't the answer, what is? What's the path forward suggested?
It's about being smarter. The real challenge, the source argues, is to design better compounds.
Better.
Learning from the mistakes of the past, understanding why certain molecules cause persistence issues or toxicity or unintended side effects, and then using that deeper knowledge to design and synthesize new molecules that still have the beneficial properties we need.
But without the downsides.
Right.
Or at least significantly reduced downsides.
Exactly. Improving the properties, making them more effective, less toxic, biodegradable perhaps, more targeted in their action, minimizing or eliminating the negative consequences while keeping the benefits.
That sounds like a massive undertaking, and it places a huge weight of responsibility on organic chemists, doesn't it?
It absolutely does. The source implies that the ongoing work is not just about discovery for discovery's sake anymore, but discovery coupled with foresight and responsibility.
Striving for that next generation of compounds.
Yes, a new generation of safer, more sustainable, more effective molecules. And the source does mention that this is a major focus of current research efforts trying to build that better future through smarter chemistry.
So wrapping this up, we've journeyed through organic chemistry from its historical roots tied to life and that debunked vital force.
To the absolutely mind-boggling, almost infinite potential number of molecules carbon can form.
And then exploring its profound dual impact, the immense benefits that shaped our modern world, alongside the serious challenges and problems that arose.
Leading us to this current focus on responsibility, on designing better, safer compounds for the future.
It really does highlight how deeply this seemingly specialized field is tangled up with almost every aspect of our daily lives, often in ways we don't even stop to think about.
It's everywhere once you start looking.
Which brings us to a final thought for you, our listener. Thinking about that vast, mostly unexplored universe of potential carbon compounds, and this ongoing need for innovation balanced with real responsibility. What areas of future discovery in organic chemistry do you think hold the most exciting promise? Or maybe, where do you see the biggest risks we need to navigate carefully? Something to ponder as you look at the chemically complex world around you.